Good morning to all of you. This is part 2 of production of X-ray and uses. Part 2, we concentrate on uses. So before we go on, there's just some note for you. Right? I'll be publishing it in YouTube so that it's more easily available to those who are not on Facebook. So you will find that very hard to find my video. Right? The easiest way is to Google my name. And then you can find all the video there. Right? If you look under like production of X-ray, you will not find it because there are others, there are more people, So mine one is hardly anyone view it so far. Okay, so you want to see so far, I've put some of the video there. If you want to follow that, you're welcome to that. Welcome to get your friend to join also. Right, just some sharing first before we start. Right, for those who want my notes, feel free to go to Facebook. Right, there's a Facebook. A-level Physics A2. You can find my video there, posted there. You can find the notes there. There's the morning physics. Or you can find the PowerPoint presentation without video. Right? That's the one. So feel free to download it. It's free to help you. To help you. You can say you can put a like there. Okay, let us start. Okay, first part we look at production of X-ray. We look at the spectrum. Remember, we need to know what are the different wavelength of X-ray that is produced. Right? Because some of the X-ray are not used to us. It will cause unnecessary damage, so that's why we have to remove it. So we have to know the spectrum first. So first part we look at production, how X-ray is produced, and then we look at the spectrum. Right? Second part, we are going to look at uses of X-ray. Before in diagnostic, we want to be able to see the different structure in the body clearly. Right? We don't want it to be blurred. Penetrating power is the ability of radiation to penetrate matter. The greater the energy of the X-ray photon, the further they can be able to penetrate through the material before complete absorb. So the radiation can be either absorbed or can pass through the material. So usually low energy is easily absorbed by the tissue. Right? You have high energy, they can pass through the tissue. So we divide X-ray into quality of X-ray, or we call the hardness of X-ray, and quantity of X-ray. Quantity, we are more interested in intensity. Keep in mind, intensity is just the number of particles, right, of photon energy hitting the body or tissue. Hard X-ray is one with high penetrating power and hence high photon energy. Right? Usually, when we say high photon energy, it's understood as high frequency. Right? And usually, the operating voltage is 100 to 150 kilovolt. Used to investigate bone fracture. Hard X-ray are attenuated by bone tissue, but suffer little attenuation by soft tissue surrounding the bone. That's what we want. We want to see the bone fracture clearly. So it must be attenuated. Attenuated, it means that it's absorbed. It's absorbed by bone tissue. But other soft tissue, the X-ray will just pass through. Right? So attenuation, we can think of it as absorption or reduce in amplitude or reduce in energy. Soft X-ray are X-ray that have much lower penetrating power. Right? Hence, low photon energy, low frequency. So usually the operating voltage is about 50 kilovolt. If it's low frequency, it must be longer wavelength. So soft X-ray, unable to pass through patient, contribute to the total radiation dose without any useful purposes. Right? No useful purposes. They contribute to heating the body, and that's why we don't want. Right? We want to avoid, because X-ray, we will learn, is ionizing radiation. So usually the soft X-ray we remove by aluminum filter, fitted across the window of the X-ray to absorb the X-ray photon. But it's of uses if we are interested in tumor and soft tissue, right? Used to make image for some soft tissue, example, growth in the liver. X-ray can give much greater difference, right? Soft X-ray can give much greater difference in relative attenuation of X-ray by different type of tissue, and thus better contrast between the two images. So if we want to distinguish between the growth in the liver, right, we have to use soft X-ray. Hard X-ray will just pass through the soft tissue and the tumor, the growth. It's the original, where they start X-ray there. Right? It's desirable to limit exposure of a patient to X-ray, as X-ray are ionizing radiation, which can damage or kill body cell. That's all we need to know. Right? We don't need to know more than that. Right? It's harmful. Ionizing radiation, damage or kill body cell. Right? You want to know more detail? Ionizing radiation is a beam of high energy particle that will remove one or more electron from an X-ray from its path. Right? If the atom is in the path of the X-ray, X-ray will remove the electron. Right? It can cause excitation. That means the particle will move to higher energy level. It can cause ionization of atom. That means the atom can lose the electron. In ionization, the atom is separated into two parts, equal and positive electric charges. Right? It form what I call ion pair. The most common ion pair is electron, and the atom without the electron, a positive ion. Right? We don't need to go so much detail. Right? It's only for those who are interested to go further. Molecular bonds are broken and abnormal chemical reaction induced. Right? If bond broken, you have to make new bonds, so it may combine with other molecule. Right? That's why we have abnormal chemical bond. Although many such changes are transient, temporarily, such changes, some of majority of it of not significant, right? But some can cause abnormal bond chemical reaction. That is the danger. Right? Most of it are just temporarily, right? Not of significant. And they discover that those who work, right, those doctors and those radiologists that work in the X-ray side tend to have more different type of disease like leukemia, cardiovascular disease, stroke, and heart disease. So you can read that yourself. Right? Note there. Okay, basic setup of X-ray imaging. You have a collimator. Right? This collimator you can push it in and push it out. That means you can limit. This is the aperture, the hole that the X-ray pass through. Control the aperture. Right? You can make it smaller or bigger. You'll see why. And then you have the grid there, anti-scatter grid. You will look into that in a while. And then you have your X-ray film or photographic plate. And that is the negative, right? The X-ray film of the human chest. And then you can see why this person, how the scissors can get into his throat there. Right? The surgeon have to save the man's life after he accidentally swallowed. I don't know how. Maybe he used his scissors to dig his teeth. Okay, how X-ray image is produced. Okay, we have tissue. This whole thing is your tissue. Think of your body. And then this is your bone. That is your X-ray film or photographic plate. As the X-ray film passes through the body, part of it is absorbed. Remember, part of it is absorbed, the rest will pass through, or we call transmitted. So usually we look at parallel beam. These are all your X-ray coming in, parallel beam. So it passes through tissue. If it's part X-ray, it passes through tissue, but the bone will absorb it, won't pass through. Right? So the image that we obtain on the film, X-ray film, is a shadow of the tissue. Right? Where this part will be, where the X-ray doesn't pass through, will be white, and this part where the X-ray pass through will be dark. Black when developed is two part there where the X-ray pass through. When the X-ray cannot pass through, we see white. Right? So X-ray beam can penetrate soft tissue, example skin and fat and muscle, with little loss of intensity, thus appear as a dark area on the photographic film. That's X-ray of the tip of the lung. Bone causes greater attenuation. Remember, greater energy loss in bone. That's why we have attenuation than soft tissue, and will appear as lighter in color on the film. You can see the bone there, the rib. Darker is the lung there because the X-ray pass through. What is produced on the film is a two-dimensional shadow of the bone and the surrounding tissue. It doesn't tell you the distance, it's just a shadow, two dimension. Right? There's a CT scan. There's your X-ray film. Right? So the X-ray, the image produced on the X-ray plate as outlined is a flat image. Right? Two-dimensional flat does not give you an impression of depth. It doesn't tell you how deep is the lung, or whether the organ is near to the skin or deep within the body. Right? We cannot see. It's not apparent. It's not clear. Quality of the shadow picture, right, which we call the image, produced on the photographic plate depends on the sharpness. Two things, sharpness and contrast. We're going to define here what is sharpness and contrast. You have to memorize the term. Sharpness. What is sharpness? Is with which edges of the structure can be seen. You can see clearly, then can differentiate. Right? These are fingers there. Right? Or I memorize it. In sharpness, a clear distinction between boundaries. You can see clearly. These are the fingers, then probably these are the skin. Right? Or we can see this is the rib, this is the lung there. The upper part is the lung. Right? That's what we want. Clear distinction between boundaries. We want blur. How to obtain sharpness in the film? Source of X-ray must be point source. That's important. Point source we'll see in a while. Or parallel beam of X-ray. Okay. A point source or parallel beam of X-ray would give a full shadow. Right? That's your point source. That one there. If you want to X-ray object, that's your object. And then there's your X-ray film. Right? The point source, we can get the extreme of the light ray. There's your ray coming through. Just pass through here. Right? Of course, there are others. Right? But we are interested in the extreme. So this is your ray. And then you will see this is the part we are interested in. Sharp shadow. Not partial shadow, just sharp shadow. That's what we want of the object. So it's sharp. But in order to achieve as sharp an image as possible, the X-ray tube is designed to generate X-ray beam with minimum width. Remember, the X-ray is determined by this target there. This target, the electron will hit this target, and then that is your beam of electron, not a point source, right? But so the idea of getting a point source is to make sure that this target is as small as possible. There's a limit to what we can do, right? We cannot have a point source. Right? So that's your beam, right? So this one from the internet will show you You can see that. That is a partial shadow of penumbra. Right? That's sharp. Sharp. Right? But if you look at that one, as this size increases, you produce shadow. You can see that. You have okay, look into that. Okay. So sharp focal spot, you have a sharp shadow. But you have an extended source, right? Remember that we are looking at the light from different places. We are interested in the extreme case there. So you can see this one is very poor already. You got this partial shadow of penumbra, which doesn't define as clearly as here. We don't know where is the shape actually. Right? So we want to avoid this case. This is sharp. This is not sharp. So what can we do? Factors in the design of X-ray apparatus that affect the sharpness. Right? We can think of that three things. TAS. You memorize it. Area of target. This one. This is the area of target. This is the X-ray tube. This is the cathode there. There is your X-ray tube. There's a target there. Area of target. Size of aperture. This one. This is called the aperture. Where the hole. Where you allow the light, the X-ray to pass through. Produced by overlapping metal plate through which the X-ray beam passes between the tube. So what is happening is, instead of that shadow there, we can put the plate there. Then collimator, metal plate there. So we can control this aperture that the X-ray will pass through. Right? This is made of metal there, collimator. Can slide in and then slide out. Same, either way. Make the aperture smaller. S stands for scatter, X-ray scatter. This we can use lead grid in front of the film to absorb the scatter X-ray. We look into that more detail. Okay, first we look at the target there. Right? You can see that. That is your target there. Small target, partial shadow only here. Right? Big target there. Here we are just drawing the ray. Right? At the maximum X-ray, of course, there are other rays we are not interested in. We're interested how they form. Right? So this one will form. That is your full shadow. That's a partial shadow. The idea of sharpness is we don't want any partial shadow at all. We want a full shadow. Right? So one key is to put aperture there. Right? Okay? Metal there. Right? To reduce the size of the partial shadow. Right? This part of the ray cannot pass through. Only that part can pass through. Effect of the area of target. Right? So the target size affect the sharpness. Using the area of target, reduce the partial shadow. Limiting the size of the aperture. Right? This one. That's the aperture. The hole that the X-ray pass through. Right? So normally we use the slide there. Right? That's a collimator. The plate there. These are metal plate there. This can slide in or slide out. This one can slide up and down. Okay, so that's collimator there. And then we have the X-ray beam coming out. So we can adjust the overlapping metal plate, control the size of the aperture that the X-ray pass through. Okay, so that's the X-ray passing through. And we can see that, yeah, instead of sometimes unknown reason, this scatter. Right? This is scatter. We don't want all this. Right? It will disturb the film. Right? We don't want the scatter. So what we can do is we can put lead there, lead grid there, so that it will absorb the scatter there. It will go through. Only those you want to go through will go through. Right? That's a lead grid. Right? That's your scatter. Use a lead grid in front of photographic plate as your film. photographic film. There's your light grid there. To absorb the scatter. Contrast. Contrast, difference in blackening between structure. Memorize. Right? Usually under X-ray, they will ask you what is contrast, what is sharpness. Contrast is due to large difference in blackening of different region and is caused by differences in attenuation coefficient. We will look into that. Right? So, to be able to see different tissue, we must have a good contrast to know that these are lung there, these are heart there. Right? We'll look into attenuation coefficient in a while. Okay, differences in brightness between bright and dark region of the image. That's what contrast is all about. You can see there. So, high contrast, low contrast. Same region of the shoulder. Right? We can see this is low, optimum is too high. Contrast or image produced on a photographic film is affected by what influence contrast? Exposure time. Not enough exposure time. Right? Penetration, X-ray, scattering. Scattering means allow the light that's not supposed to go into the region, go into other region, right? Disturbing the image that we obtain. Improving contrast. In order to improve contrast, a contrasting medium may be used. For example, the stomach may be examined by giving a patient a drink of barium sulfate. As I shared earlier, when I went to New Zealand to study, I drink a lot. Milk is cheap there, 11 cents a bottle. So of course you drink milk, but when you drink milk, most of us Asians don't have the enzyme anymore after a certain age. So when we drink milk, we get into trouble. Right? So see the doctors many times cannot find a solution. So he sent me to Wellington Hospital to check my stomach, see what is wrong. Because I see him so many times, he give me food for he gave me pill for gastric, and then I told him I got too awful food poisoning. So he was concerned what's happening in the stomach there. Right? So they give me barium sulfate in milk, and then they examined it. Right? Of course, it was free. When I was in New Zealand, it was free. I didn't realize that. Or we want to see the blood vessel, we need a contrasting medium that absorbs strongly the X-ray radiation and will be injected into the bloodstream. Right? Or it can be improved by backing the photographic plate with fluorescent material. Right? The X-ray plus through the fluorescent material will give out light, so it will improve the contrast. Know what is given in your formula sheet. Okay, you can use that one. Radioactive decay, you can use the same idea as radioactive decay, which you can study this under radioactive decay slide video. Okay, so roughly this one give a pictorial view, right? The X-ray going in, attenuation means some of it is absorbed, gas is coming out, gas energy is coming out. Attenuation of X-ray is the degree of absorption of X-ray by the body tissue, or we call it decrease in energy, or decrease in amplitude, or decrease in power. Doesn't matter, any of the term can be used. Examiner accept it. Right? This one you have to memorize. If the examiner asks you what is linear absorption coefficient, memorize the whole thing. Like that formula. Okay. I naught, yes, I naught. The intensity before it enters the tissue or absorber. K or mu, sometimes called K, called mu, or called lambda. Linear absorption coefficient. Right? This is the material. It has a mu there. And then X is the thickness of the absorber. And intensity after passing through, I is the intensity after passing through the absorber. For parallel beam or radiation, intensity of radiation after passing through the absorber is given by this formula. And mu naught is called the linear absorption coefficient. Right? Sometimes people use lambda or linear attenuation coefficient. Right? The unit is always per meter. Right? There's a negative sign there. Per meter. Right? Because this is in meter, this must be per meter. Or if this is in cm, this must be per cm. Okay, half value thickness. Right? It's just a half-life in radioactivity. It's ln2 divided by mu. Yeah, the probability constant in radioactivity. Half-life is the thickness of a medium to reduce the transmitted intensity to half the initial value. Right? The thickness of a material where the intensity is reduced to half. And it's a constant for a particular energy. Different type of tissue absorb radiation to different extent. Remember, the half-life is only good for a particular energy of X-ray. You see in the world. Right? So that is what it means by attenuation. If you before it enters 100% at one half thickness, half value thickness, 50, decrease to 50%. Another half value thickness, another half of it, half of 50 is 25, and so on. Some approximate value of linear attenuation coefficient, right? You can see that copper, this one is for particular energy only, right? You have to compare with the same energy. Copper is quite high, metal, bone is also quite high. Water and fat, very small. So we can see that mu depends on the type of material. Bone is a better absorber X-ray and fresh. So mu is high. Also depends on energy of the X-ray photon. Okay, you can see from here. Can we learn from this is for bone, this part for muscle, this maximum X-ray energy that we use, right, for bone and muscle. Can we learn from that? We learn that the absorption coefficient mu depends on energy. Right? As we increase energy, this smaller energy, high energy, you can see that this one, if we look at particular bone, this one decreases, mu decreases, this one also, mu decreases, right? Because high energy, the X-ray can pass through easily. Low energy is better to differentiate between bone and muscle than high energy. It will give good contrast. You can see that if we use high energy, these two are relatively quite similar, right? Almost the same value. But if we use 50, you can see that there's a difference, 6 times different. Right? This one is 3 times different only. This is 6 times different. Right? Roughly. So 4 mega electron volt, the difference in mu is not that significant. So we won't use that. Because bone and muscle are the same. We cannot see the contrast there. Okay, so attenuation by different body tissue depends on density of the tissue, thickness of the tissue. Right? The thicker it is, the more it can absorb before the radiation pass through. Atomic number of the elements that make up the tissue. When a beam will actually pass through matter, such as a body, tissue, energy is given to the tissue, and the intensity of the beam is reduced, or we call it attenuated. Right? It's absorbed. So the intensity coming out finally from the body or tissue is smaller. Okay, this one show you the same thing, half value thickness, right, for different energy. Right? It changes. It's only constant for a particular energy. And we can see that half value thickness for high energy tends to be larger. Right? So linear absorption coefficient depends on energy of X-ray and half value thickness also. Okay, this one you should be able to do that. Explain why continuous spectrum of wavelength is produced. This one should be able to prove. Electromagnetic radiation is produced when a charged particle is accelerated. This is the production side. Wavelength depends on the magnitude of acceleration. Okay? It means it depends on the X-ray energy. Electrons have a distribution of acceleration. So it will give out different energy and different energy of your X-ray. So we got a continuous spectrum. Spectrum have a sharp cut-off wavelength. Yeah, you should be able to explain that. Right? When electron loses all its energy in one collision, then there's the X-ray photon. There's the kinetic energy of the electron. Or when the energy of the electron produces a single photon. Right? One electron gives its energy completely to produce one X-ray photon. Let's explain the short wavelength. Right? This one is to teach you how to answer the question. Explain the principle behind the use of X-ray for imaging internal body structure. Right? We have gone through part 1, so you should be able to do that. Right? Sorry, this one was done earlier, so you should be able to summarize it. X-ray beam directed through the body onto a detector. Right? X-ray pass through the body, and behind the body is the detector. Detector is always a photographic film. Different tissue absorb the beam by different amount, giving shadow images of structure. In contrast, large differences in blackening of different region due to different attenuation coefficient. In sharpness, the edges can be clearly distinguished. So depend on the mark that is required, that's given in the question. You may have to include all these points there when you're answering the question. Okay, let's just summarize. Right? Quality, X-ray, high penetrating power. So it means high photon energy. Soft X-ray, low penetrating power, just pass through the tissue. Right? So you have low photon energy, and you have a photographic film. There's a lead shield. Just to summarize what we have learned. That's all. Right? And then we know that X-ray radiation is hazard to health. Right? Dangerous. So we want to keep exposing ourselves as little as possible. That's why we don't spend a long time when we X-ray our chest, just as short as possible. Right? Collimator controls the size of the aperture, the hole where the X-ray pass through. Right? Aluminum filter to reduce the soft X-ray. Okay? Sharpness, a clear distinction between boundaries. Right? Point source or parabeam will give a full shadow, give it a sharp image. So one way to improve sharpness is to reduce the target size, reduce the aperture size, right? Make the aperture smaller, cut out the partial shadow, and also scatter. Right? We don't want the scatter ray disturb our image, so we use electric to absorb it. Contrast, we want differences in blackening between structure. You can use contrasting material. Right? If the tissue have, you want to see clearly what's happening in the stomach, like in myself. Right? Anything happen to the stomach, you can have contrasting material, then barium sulfate, add to milk, and then we drink it. And then we need to know how to use this formula. So next part, we will solve some partial question. Right? Let's look at some partial question. We will solve. Okay. Attenuation coefficient of bone is 600 per meter. X-ray of energy 20 kilo electron volt. A beam of such X-ray has an intensity of 20 watt per meter square. Calculate the intensity of the beam after passing through 4 millimeter thickness of bone. So you can either change this to meter or you can change this per millimeter. The two must be the same. You need that. Okay, cannot mix the unit. So 600 becomes your 600 over 1 meter. Right? 1 meter is 1000 millimeter. So by 1000, so you can convert that to 0.6 per millimeter. And use the formula. Right? Remember, go to formula sheet you've forgotten. Except just change the symbol. I is not the number. Right? I is the intensity equals to right? That 20. Not this one. This is the energy. We are interested in intensity. How much the intensity is reduced. This is a distraction, that's all. E, right? That one, we change it to millimeter per millimeter, 0.6. And then the thickness is 4. Put inside there, calculate out. Explain how hardness of X-ray is controlled by accelerating voltage in the U tube, in the X-ray tube. Hardness depends on energy of X-ray. Right? Changing the voltage changes the energy or speed of the electron. Changing electron energy changes the maximum X-ray photon. Right? Remember, the maximum energy of the photon of X-ray depends on your accelerating potential. Larger accelerating potential, you give more kinetic energy to the electron. So the X-ray also will be X-ray energy will also be larger. Right? They will ask you, then now use the formula. They are very kind to give you the formula. The attenuation of parabeam of radiation is given by the expression. Mu naught is the linear attenuation coefficient. X is the thickness of the material. What is meant by attenuation? Yes. And we will encounter this very common from now onwards. What is attenuation? Right? Remember, loss of power, loss of energy, or loss of intensity, or decrease in amplitude. Why the expression applies only to parallel beam? Intensity changes when beam is not parallel. Okay? Some have to travel longer distance. Decreases when beam is divergent. Okay? Different distance they have to travel. Okay. Yes, using the Planck formula previously. The linear attenuation for X-ray in the bone is 2.9 and soft tissue is this one. Calculate for X-ray beam the ratio, right? Fraction of intensity transmitted through bone, that's 2 cm, 2.5 cm, and then transmitted to soft tissue of thickness 6.0. So you just use this formula, that's all. Right? Very kind, just straightforward substitution only. Your mu, right? This one is for bone. Then for bone, this is your bone, 2.9. Unit the same, per cm, this cm, okay, put 2.5 cm. And this is for your soft tissue, and that's your 6 cm. And the other rest is just your calculator. Is your calculator. Right? We are just using multiplying indices. Right? Where you multiply them, we just add them up. Okay, this is quite a form. Sometimes it may come out. Right? Okay. They ask you to derive, or you just use the equation. No? If you have not only one material, two material, right? This is the original intensity. This is the intensity coming out. There's the thickness of tissue X. There's the thickness of tissue, the other tissue S. Right? Each tissue have different absorption coefficient, mu and this K. And you are asked to show that equation. Okay, let's look at one. The first tissue, absorption coefficient, mu naught, mu, and then that's material one. That is what goes in. That is what come out, transmitted intensity. That's the thickness. So you should be able to write the equation down. Right? Equation down. Then after that, we have another thickness. There is K there, material 2. Remember, I1 is transmitted from the red one, but it's going into the gray one. And the thickness is S. So coming out will be your I. Okay? So I1 is the original beam now. I is the one coming out. Okay, so you should be able to write the formula. I1 is the initial, coming out is the I, and then it pass through this material, so it's minus Ks. And I1 from this equation, replace it with this one. That's what we get. Right? So if they didn't ask you to derive, don't derive, just memorize how to use the formula. Sharpness, memorize. How well the edges of the structure are defined, contrast, different in degree of blackening between structure. Memorize. Right? This is 213, June paper 41. What causes the loss of sharpness of an X-ray image? Scattering of photon in tissue. Right? Or if we don't use grid, we don't use collimator. Right? Because the target is too wide, it's not a point source. Right? So they accept all these answer. Large penumbra. Penumbra is a partial shadow. Or large area of the anode, or usually we call it large area of target lah, or beam, white beam, either one. Right? It describe the beam. So all because of the target. Target is white. Right? Large pixel size. Okay, and always after all the definition, they will need to calculate data for linear attenuation, absorption, mu of X-ray photon are given for bone and for muscle. Parallel beam of X-ray is incident separately on a thickness of 3.5 cm of bone and 8.0 cm of muscle. Intensity of X-ray transmitting through bone, intensity of X-ray beam transmitted through muscle. This is a value that's given. So remember this formula? Right? So there's the original intensity. We will cancel off. And then we are looking for bone. So bone, that is your bone. Attenuation coefficient, minus 2.85. Thickness 3.5. And then intensity transmitted through muscle. Look at attenuation coefficient of muscle, that one, 0.95. And 8 cm. Then we get 0.093. Use your answer in 1 to suggest whether X-ray image of the bone and muscle would show good or poor contrast. You can see that comparison. This must be very large, very small. There's a wide difference there. So good contrast. Large difference in intensity or ratio, less than 1. 1 means it's the same intensity. So good contrast. The two of them, large intensity different. That's why we see the smaller fraction less than 1. Or you can describe in terms of the fraction less than 1. So good contrast. Okay, so that's the end. The next video will show you CT scan. So we'll end here.